We're really thrilled to have Odd van der Vaart as our next speaker. He's been a giant in the mathematical statistics field. He got his PhD from University of Leiden in mathematics in 1987. And he was at, I don't know how to pronounce it, VRIJE University in Amsterdam. We'll ask Odd. And then at Leiden University for a number of years. And now he's at TU Delft as a professor of statistics. I suggested people for the organizers to invite where I was especially curious about work that they have done. In this case, he's worked on many things. The one that I have been most curious about is his work on Bayesian asymptotics. He has a paper with Ghoshal and Ghosh on convergence rates of posterior distributions in the Annals of Statistics from 2000. And I love the history of that topic. It goes back to Lecam and Schwartz and ideas of testing against complements of Kullback-Leibler balls. We're going to learn about other types of balls being appropriate. And or testing against balls of other types if you want to look at concentration. And in high dimensions, there's value to neglect a set of points outside of that ball. And that's about consistency, and Odd took it so much further, working out under suitable conditions what the rates would be. So he's a frequent invitee. I think you were here for either John or David's retirement parties, and so successful we invited you back. So take it away, Odd.
Well, thank you very much. Let me start also with the memory of Andrew then. I think my first time that I met Andrew was at MSRI in 1992, Andrew said yesterday. There was a semester at MSRI which had actually two parts. One part was on empirical processes that was organized by David Pollard, and I was, I think, more in the other part, which was on semi-parametrics. And my recollection of Andrew is that he gave me a ride. MSRI is on top of the hill in Berkeley, and it's quite high. It's really perched up there, and cycling up is really big work, which I did sometime. But Andrew gave me a ride down one day, and that's not so special. Yeah. That's not so special, maybe, but I definitely remember that in this short ride down to the campus, Andrew told me everything that was important about statistics, and all things I didn't know anything about. So up there, I was in semi-parametrics, and I thought I was on the top of that subject. But Andrew told me about lots of other stuff, and well, my later subject, as Andrew mentioned, is on Bayesian nonparametrics, and then I really crossed Andrew's path. So that the talk today is somewhat related to that, or it is about Bayesian nonparametric, but then in the setting of inverse problems. The data we get is some yn, and yn is some signal plus noise, and the noise, I just wrote something formal 1 over square root n w dot. It's going to be Gaussian noise, and like you have n observations with noise 1, or you can make it a formal white noise model if you like. The interesting thing is the signal, the u is a solution to a partial differential equation that depends on some parameter f, so I write u sub f. And in the title I have inverse. Well, that is that uf to f, we need to go from uf to f because we are interested in f. That's not a differentiable map. And I also have nonlinear in the title, and that is that the map from f to uf in many applications is nonlinear. If you want a concrete equation, this is the simplest one that I'll use for illustration. A half times the Laplacian of u is f times u. And you can see that is a linear equation in u, so PDE specialists will say that's a linear equation, but actually we're going the inverse way. We're interested in going from the solution to f, and that is a nonlinear map, very simple. Here you can just solve f is the half Laplacian divided by u, that gets you the f back. Now, to estimate the f with noisy data, you can do regularization, which would be like least squares, and then you add a penalty of your choice with a smoothing parameter, and you minimize that. What I'm going to do is what you could call Bayesian regularization. You do an ordinary Bayesian approach where you put a prior on the f, and so then you get a posterior distribution, f given yn, in the usual way, and if you wish to turn that in a point estimator, you could take the posterior mean. There is a connection between these two. There are multiple connections. Maybe the best connection is this one. If you would take a Gaussian prior for f, then they will come with some reproducing kernel Hilbert space, and that has a norm. And if you take the penalty to be the square of that norm, then the posterior mode, if you define that in the correct way, that's not completely trivial here because f is infinite dimensional. There's not something like a neutral back measure. But if you define this in the correct way, then the posterior mode is the regularized estimator. However, the posterior is a full distribution over functions, so it also has, say, a second characteristic, a spread, and you would like to use the spread for uncertainty quantification. Nowadays, it happens a lot. People say, okay, I have my favorite estimation procedure, but I need uncertainty quantification. Oh, let's put a prior on the parameter, and then we have a Bayesian machine that gives you a posterior, and so some spread. The question is, does that work, and under what conditions does that work? Here are some other examples of inverse problems. I won't go through the list. These are problems that have been tackled in more or less in the way that I'm also going to talk about it. Two references that are a good starting point. The first one is by Andrew Stewart, which is a very long paper. And Andrew is an applied analyst, and he propagated the Bayesian approach for uncertainty quantification. And the second is a book, lecture notes by Richard Nicol, who is from statistics, and he developed some of the theoretical results in the area. There's not really a lot yet, and it's a bit like also you do a new equation, you have a new problem. That's true for PDE people, but it also seems to be a bit true for us statisticians. The pictures, you have recognized Antarctica. This is about the flow of the ice shield on Antarctica that's sitting on the landmass, and there's friction below. And the inverse problem is you see the ice flow, and you would like to estimate this friction parameter. As soon as you know that, then you can calculate how the ice will flow further. And if it would be stable, you could also use that for climate science and predict what the world will be like in 2100. This was done by the Gaussian prior, and it's published in a paper by Isaac et al. In Applied Physics journal. So these things are really applied. I mean, this is really things that people do in practice. Okay, so again, we do full ordinary Bayes. That means f will be coming from a prior. We have a likelihood, yn given f, that will be a Gaussian likelihood in my case because of Gaussian noise. And then we get the posterior distribution, which here is just given by Bayes' rule. To show you these two communities, it's nice to say that some of the applied analysts think that Andrew Stewart proved Bayes' rule in 2010. But I must say, we are the same. We come from statistics, and we have no clue about PDEs. So it's interesting that these two communities get together. Then computation is a big issue. It's typically MCMC, and the particular favorite here is called preconditions Crank-Nicholson, which is something like a Langevin sampler. It's very important, and it's difficult. If I have time at the end, I'll talk a bit about our own work with doing distributed posteriors, which is to split the data and speed up the computation somewhat. What I'll be mostly talking about is frequentist Bayesian theory, as it's called, And then there are two issues. First question is, does the posterior really recover a true signal, if there is one? So I'm stepping out of the Bayesian paradigm. I'm not assuming anymore here at the bottom of the slide that f is really coming from the prior, because if that were the case, then doing the Bayesian stuff with the prior that you like, that is absolutely fine thing to do. But now we assume that there is actually a true function f naught, and we just using the Bayesian method to get some posterior distribution that hopefully recovers that true f naught. Then contraction rate is saying that the posterior puts most of its mass around f naught at a distance no more than some epsilon n, and we're interested in how fast can epsilon n go to zero, so that is still true. That's a measure of quality, say, of the prior. And Andrew wrote a paper giving conditions so that there exists, say, some epsilon n going to zero. And so we later, that's what Andrew mentioned, we later went into, well, how fast can epsilon n then go down to zero? Can we characterize that too? The other aspect is uncertainty quantification. And there's much less insight even today in uncertainty quantification than in contraction rates. Contraction rates we have in many problems, uncertainty quantification in hardly any. That is the question, is the spread in the posterior, does that give you a good indication of what is the error margin that you should take, say, in the posterior mean? What you could do to quantify that is you take a central set in the posterior, C and Yn, depending on the data, of almost all probabilities, say 95%. That will give you the order at which spread is. And then you wonder, is that a confidence set? Well, actually, I was very modest. Confidence set would mean also 95%. No way, these things are really different. There's no connection in this non-parametric situation. I have f is a infinite dimensional parameter. There's no exact connection between the two. So I'm already happy if it is bounded away from zero, so that you don't have a way too narrow set that is not capturing the f naught at all. This is our contribution here, that an approach to solve these nonlinear inverse problems by linear methods. And it sounds a bit funny, but what we do is we assume that we can isolate some linear operator, and think of the Laplacian in this example that I gave, a linear operator, so that we can write the PDE in the form linear operator of UF. Let's see, do I have a pointer? Yeah, here. So linear operator of UF is some function of f and UF, and that function is a deterministic, well, it could be an operator, doesn't have to be pointwise or anyway, but this could be the nonlinear thing, and that is then deterministic. For instance, this Schrödinger equation that I already showed you, the L can be taken the Laplacian, and the C FUF is 2 times FUF. Pretty simple. So then that is always possible, of course, to find the linear operator, your boundary condition. But we will also assume that we can then recover the F from LUF by a nice map E, and E basically should be Lipschitz. So the linear operator should be rich enough so that it characterizes the problem, so that the F can then, by a deterministic map, be recovered, maintaining, say, the quality of estimation. If we can estimate LUF, then we can estimate F. So in the example of the Schröder, the E map is just taking the Laplacian divided by 2UF. So if you can estimate the Laplacian, then with the boundary condition you also know UF, and that's a nice map. As long as UF is bounded away from zero, it's very Lipschitz, and so we are in business. Then the problem becomes to recover the Laplacian, and that is linear. How do we do that? Well, then we just rewrite the equation, which was Yn is UF plus noise, as Yn is k LUF plus noise, where k is just the inverse of L. And L is a differential operator, and k will then be a smoothing operator. Well, actually, I'm making it a bit too simple here, because we have these boundary conditions as well. Then the k that I just wrote would not be a linear operator, because the boundary conditions, if it's non-homogeneous, that wouldn't be linear. So we do one step more. We get rid of the boundary conditions by first finding a function g tilde on the full domain that satisfies the boundary condition and satisfies the homogeneous problem, or no, yeah, the problem. Well, it's this, yeah, the problem that operator is 0. So, and then we can make the k to be the inverse in the homogeneous problem. Now, homogeneous understood as having 0 boundary conditions. This k is the inverse of L, and it's linear, and then we can rewrite UF as k LUF plus g tilde, and we could define Yn tilde, a new observation, which is Yn minus g tilde, and that is k LUF plus 1 over square root WP. The g tilde would be known because we assume the boundary condition is known, and so the Yn tilde is just like an observation. And then we get this setting in this box. We think of the L of u as a new function, v. We can recover the f from that function, and we get 2 problems, a linear problem and the original nonlinear problem. The original nonlinear problem gets a posterior on f. That's what we are interested in. But I can first solve this linear problem, which gives a posterior on the v, and that's based on this linear problem. And then you just map v up the push forward measure to go to the f. If you can do that, then the properties of the linear problem will transform into the properties of the nonlinear problem. For instance, a contraction rate. If I have a contraction rate for the linear problem and E is Lipschitz in the correct way, then the contraction rate is also a contraction rate for the nonlinear problem. Uncertainty quantification. If I just take the push-forward credible set, that's what is written here in formulas. So C n tilde, Y n tilde is the credible set, the central set in the posterior in the linear problem, and I push it forward to the nonlinear problem, then you retain the credible and confidence set levels just by the push-forward property. And so you have solved, in a way, also the nonlinear problem. Okay, this connection, that works for every prior on F. So I can put a prior on F, and then I get a prior on the LUF, the V, in the linear problem. However, if I want to make effective use of this linearity, it's nice to have a standard prior in the linear problem. And there the nonlinearity, of course, might be bothersome. If I really were convinced that a Gaussian prior would be the right thing for the F, a real Bayesian, and then my idea is that really F comes from a Gaussian distribution, then the push forward on the V, the LUF, will be not Gaussian because it's a nonlinear map. And it's a lot easier to put a prior on the LUF, for instance, a Gaussian prior on something else, or even use an eigenexpansion to get a prior in this linear problem. So it works better if we use standard priors. And that might be a disadvantage, but on the other hand, it's really impossible in this non-parametric Bayesian situation to have a feel of what your prior means, so it doesn't seem to hurt too much to make this step. Second, we need some good results for linear problems, and there are some results readily available, but we need a bit more to make sure that this EMAP works fine in our setting. I have 3 slides on the linear problem, and I'll quickly go through some of the things that's been done. This was done starting in the 2010s or so, and this is our latest little thing we did. So linear problem, K is a linear operator. typically compact, so the inverse is unbounded. And we put the situation in taking an orthonormal base of L2 of the domain, and we have a scale of smoothness norms. If this would be the Fourier basis, this would be roughly the Sobolev scale, but you can do something more general here. Then the big assumption about the operator is that it's smoothing in the sense that if you take a function v that is in the scale at negative regularity, then once you apply the k to that function, you get just to the L2 norm. And that has a parameter p that is the index of inverseness of the k. Then here is the theorem about the posterior for v getting from this data. And the theorem is stated in terms of something called the Glerkin projection. Glerkin method is something developed in inverse problems in applied math. It has nothing to do with statistics. It's just some way of recovering a function from the image of a function on v. So it's mapping, say, from kv you go to v. We will not use that as a method to numerically derive some solution, because I'm going to do this the Bayesian method, but I do use it to frame the conditions on the prior under which the Bayesian method works. Roughly, if the prior cooperates nicely with this Glerkin projection, then the Bayesian method will work. What is this Glerkin projection? It's a very simple thing. You have a function f. It's, say, in L2, or the smoothness G0. It's mapped to the image kf, and then we want to go back. But rather than just inverting k and go back immediately, which is bad because k inverse will be not a continuous operator, you first simplify the kf by projecting it down on a finite dimensional space, namely the image of the linear span of these basis functions. That should have been the hi's here. Sorry, I have e's, but these should be the h's. So use one basis. So you first project it down, and then you do the inverse map. So I do assume that you have identification under the k, so that there is a map, or at least under these finite dimensional spaces. And that's just a nice numerical method. Now the theorem on the posterior, so it gives a contraction rate eta n on the posterior. It has two conditions on the prior. And the first condition is one that we've been known for a while, and that is basically the condition for recovering kv from the data. And that's like a regression problem. Yn is a regression function plus noise. Then to recover the function kv with the posterior, you get something called a small ball probability. And that is the amount of mass that the prior puts in a ball of radius epsilon n around kv0. And that should be at least e to the minus n epsilon squared, up to some constant. And that actually characterizes often the posterior contraction of the posterior of kv. But we're not interested in kv, we're interested in v. So we also have to make this inverse map. And for that we use this Glerkin projection. And the second condition has an eta n rate in there, and it says that the prior should put most of its mass. Oh. Yeah, that's inequality is the wrong way. So the prior puts most on the mass on, so this should be, this one should be around. So this should be almost mass 1. So this is what you're allowed to miss. It shouldn't be a small probability, or you could say bigger here. So that the v, the function v, is close to its Glerkin projection. And if that is the case, then you get a rate epsilon n. Now the Glerkin projection has a dimension, so there's also some equations you have to satisfy with the dimension and choose the dimensions. Okay. I have two more slides which specialize this prior. First to a Gaussian prior. So if you take a series expansion and you put Gaussian priors on the coefficients, then you get the kind of usual rates. Here, there is a fixed smoothness on the Gaussian priors, and then the smoothness pops up in the rate. So this is not the minimax rate, but it is the rate you get with the prior alpha when the truth is beta smooth. And something that is important for us also is that we get a rate here in a smoothness norm. So if delta is positive, this is a stronger result than just in L2. And that is important for the application that we do where we need to do this map. I get a 5-minute sign, but my watch now says 23 minutes. So I think I started a bit late, but I'll try to finish. We also get some result in the uniform norm here, which is kind of special because that is typically very hard to get. But in this setting, it was again important, for instance, to keep this function u bounded away from 0 for the inverse map again. Third slide on this is making one step further. Before I had a prior with a fixed regularity alpha, but now alpha itself get a prior, or you might determine alpha by the empirical Bayes method, so make it data dependent, and then we get the minimax rate for the problem. We get uniform consistency. We also now have results on the coverage, and it says that if the true function is a polished tail function, and that is a concept that we introduced in the direct problem before, then we have coverage going to 1, so bounded away from 0, even going to 1. So we cover more, but that is basically also because we have put a constant in here. The more complete statement would be that if the m here is large enough, and the psi hat is exactly giving you the Bayesian coverage, 95%, then you get even more than you want. But it's sort of indication that these sets you get from the prior have the right order of magnitude. In terms of exact coverage, it's hopeless. Polished tail, I think I had 2 slides, but I'll skip that, what that is. Here's an example with the Schrödinger equation. So that's that system. There, the eigenbasis, if you take the domain to be the unit cube, then the eigenbasis can be used and makes it all very simple, and we get all the usual range that results that we want for this case. The other, I have some pictures. This is on dimension 1, where you can see the bands are in green, the truth is in black, I think, and you also see some dashed curves. That is the posterior that sort of gives you some idea of the spread. Seems to work. We implemented it also with a spline prior. Seems to work too, but we haven't any theoretical results on that. Works in 2 dimensions. This is the unit square as a domain, and color-coded true function here, posterior mean here, and these are then 2 kind of quantiles in the posterior color-coded. So the posterior mean is in between the 3rd and the 4th column, and the idea would be that the truth should also between sort of the 3rd and the 4th column. The rows here are different sample sizes, and so you see it somewhat coming better later with higher sample sizes. Other examples, we've done so far all the examples that have been done by other means. So it seems that you can define these operators in some generality. And I skip those details. No, maybe I should tell you one thing being, so this is a well-known equation, the Darcy equation, the Darcy flow equation. Then there is no map explicitly of this solution map, but one has to do a numerical implementation, which we also did using results, earlier ideas from numerical analysis, and it can be implemented efficiently, even in that case. I conclude with a few remarks on the distributed posterior. So it's still a lot of calculations, even in this linear case, and if you're in 2 dimensions, it's still takes hours on a small laptop to compute. So one might try to speed it up. And one way of doing that is to divide up the data in batches. Say we have a regression problem with n points, and then we make m batches of size n over m. And on each batch, we compute a posterior distribution as before. Then we get m posterior distributions, say, written like this. And we have to combine them. And the two ways of combining them, one is depends on how you made the batches. If you divided the data in random batches, then it was found out by Szabo and von Santen that it still works, but you should scale the prior before you start the priors in the batches you should scale them up by square root m, square root of the number of batches, and then you take the average of the things you get from the batches. Another idea is to make spatial batches. So in the regression problem, you divide the x's in where they fall in the space, and then you take from the posteriors and you take the spatial posterior appropriate to the xj's. This table seems to indicate that the benchmark, which is computing the full posterior, is and that is just in the Gaussian case. In the linear case, so simple. It's not MCMC. Takes a lot of time, and if you do this distributed case, then it saves a real lot of time. So 1,000 observations, and with 5 batches, you go from 15 to 2, but 10,000 and 100 batches, you go really from thing. Does this work? Yeah, so last remark to say that if you want to do a prior with a data-driven length scale, like putting a prior on this alpha, you should use spatially defined batches because the other method cannot recover the information from the batch and go back and get the bandwidth right. Okay, thank you.
Thank you very much. Are there questions or comments?
So does the problem, at the end you said you want to use the spatial instead of the rescaling. The rescaling doesn't recover.
In the spatial, we do not rescale. Oh no, sorry. Yeah, we have the length scale. Yeah.
But in the rescaling, how come you don't recover with the rescaling?
In the spatial, you do, but.
Spatial you do, but if you didn't do spatial,
to have a proper formulation, which I didn't do, but these other people did. It's about communication, so you have to compute the correct bandwidth from the problem, and that is a trade-off between the number of observations you have and the perceived smoothness by the procedure. And of course, it's true that if every separate problem can send all the information to some central entity and then do the bandwidth choice there, then it works. But if you limit the communication from the batches to the truth, then you cannot make this trade-off.
Yeah, the rescaling is bizarre.
Yeah, I have a question. So we have these nice Gaussian priors, and they can be tuned to knowledge of the beta, the smoothness presumed of the function. But also the Bayesian methodology gives a lot of flexibility to try to build a prior that could work for all beta. Have you explored that? Maybe a mixture of the Gaussian priors?
Yes. So I had one example where we have this alpha, that is the Gaussian prior that gives the smoothness, and then you put a prior on the alpha, or you do
prior on the alpha. So that was covered. Thank you.
Or what is done more often is that you have a Gaussian process and you think of it as a function, and then you change the length scale. So you shrink it or extend it, and you can do that by putting a prior on the length scale, or again do empirical Bayes. Yeah.
And you went even farther here to have location-dependent smoothness in this diagram up here right now.
Yeah.
Good.
Yeah, so that has been explored. Yeah.
Good. Anything else? All right, we reconvene at 11:30. Thank you.